My name is John Peck. I work with Algorithmia. I'm a developer advocate with them and a software developer. And I moved into advocacy about 2.5 years ago because it turns out that I enjoy talking more than I like coding at this age, which probably says something bad about me. But I try to keep coding as much as I can. In any case, this presentation's at bit.ly/OSCON 19 case sensitive. And you can find me at PECKJON on just about every social media. I don't need to go over a lot of this, because all of you who've been here since this morning have heard this 15 times over, right? We're all having very, very similar problems and solving them in lots of different ways. But the fundamentals are, all of us are hitting that point where we're coming out of having just 1 or 2 models. We're maybe training them locally. We've stood up our own independent server. And now we need an entire system for managing lots and lots of heterogeneous models. Really reducing that time to deploy, separating DevOps and ML concerns, all of that good stuff, right? At Algorithmia, we went through that. We built our own framework for doing that. I'm going to take you through some of that. Yay, yet another framework. But then we also made it a service that anyone else can come in and use, grab, and put their own models up there. At this point in time, we've got something like 9,000 different models running. Each of those has about 10 versions in production, so about 90,000 different versions of models swapping in and out as needed. And we have a community of about 95,000 developers. They're all very different. They're very unpredictable. Their usage patterns are very different. The models they develop are very, very different, which provides for an interesting challenge. Each one might be called, once a year or 1,000 times a second. There's a huge amount of variance across our ecosystem. All of those, the needs that we were trying to fix for those users were auto-deployment, discoverability of their models, consistently really low latency across them, and a common API across all of those different models so that you can actually have composability, the ability to pipeline from one algorithm into another, and fine-grained security standards, all of that across them. So some of the stuff you all have seen already, you're dealing with specialized hardware, generally GPUs at most. Most of us aren't quite in the TPU world yet, though I might be surprised. Actually, show of hands, anyone using TPUs in their production workloads? Nice, very cool. All right, called from lots of different devices and architectures. And this really presents a problem for most DevOps teams. They're not used to this sort of thing, right? We're presenting them with new challenges and what kinds of hardware we need, what characteristics we need operating it. And then on top of that, we're getting restrictions from above. Things like, hey, stringent security and access controls and compliance and audit trails and logging. We've seen a lot of that today. And we end up either with lots of redundant work across those teams, or data scientists being asked to take on DevOps tasks, or DevOps people having to learn specific ML frameworks, if not necessarily how to do things like, say, train models in them. So nuts and bolts is just because we can do machine learning doesn't mean we can do production machine learning. These are completely different things. A really fun quote from a friend of mine: expecting your engineering DevOps team to deploy ML models is like showing up at SeaWorld with a giraffe, because they already handle large mammals, right? So completely different worlds. Just because they can do DevOps doesn't mean machine learning DevOps. So just to put a fun metaphor on this, what we said is, this is sort of like the history of operating systems, right? I have a feeling I'm getting feedback off that mic, but it might just be, okay, cool. So an operating system itself, when you think about it as its core, right? It provides this common functionality needed by many different programs. It standardizes these conventions across them so they're easier to work with. It presents high-level abstractions. And the evolution of operating systems themselves can kind of instruct us as to what that evolution might look like in the world of machine learning, right? So we started off with basic punch cards, the ability to run one program at a time. Unix comes along, we get multi-tenancy, we get composability across different programs, the ability to pipe from one thing to another, something we want to do with our different models. We get hardware abstraction as DOS comes along, and so it doesn't really matter what the underlying hardware is. The way that you address a program, the way that you address a file even becomes standardized across different pieces of hardware. We get a GUI. right? Windows, Mac, obviously some of the biggest ones that many of us would prefer to play around in various Linux environments. And that really makes things more accessible to every user out there. Plus it gives us the ability to do just very easy, simple things like visually see state of our different programs at the same time and see how they're interacting. And then something that people don't necessarily think of as an evolution in operating systems, but we actually think is pretty critical. iOS and Android come along. And they, because of the way the app stores are integrated, change the game on how we add programs, new programs other people have built into our environment. It's no longer go out, find it, search for the one that's compatible with your particular OS, download it, add in whatever else you have to get it running, install that thing locally on your machine, and then you're executing it. The iOS and Android experience, even though under the hood it is that, to the end user is, I want to do a thing. Okay, let's search for how to do that thing. Oh, there's an app that does it. Click, and I'm running it. It makes that experience of conceptualization of the thing I want to do, right down to actual execution, seamless. So, to get into just how we're going to build this out, let's take one quick look at training versus production, right? And I should say I'm only going to focus on the actual production side of things here, right? I'm not going to focus on the training side of the universe at all right now. That's a bit of a different game. So training has this really long compute cycle. It's got fixed load across the entire thing. You're basically just trying to hit that as fast as you can to get your model trained up, pumping that data in, computing as quickly as you're able. It's stateful, of course. You train out your model, you get back the model. That model is useful for future things. That's your state. Generally speaking, it's single user, though you can have multi-user training systems. And that really, it's in the camp of the data scientists and the machine learning developers, right? They're building it, they're iterating over this, and then this model is ready for production. We've seen lots of different ways that can happen. Obviously, there's retraining steps, et cetera. But the nuts and bolts is you're getting a model, and you're going to actually put it out there to be hosted. Inference, prediction, completely different set of characteristics, right? Really short compute bursts. Generally speaking, you're trying to satisfy a user's request in less than a millisecond, 10 milliseconds, 100 milliseconds for some systems. If you're doing really long batch runs, yes, you may be talking longer times. But generally, short, bursty activity. It's elastic. There's lots of variance. People coming in, doing different things at different times. It's stateless. You make one prediction, it's throwaway after that. Yeah, you'll have logging, auditing, you may collect some data for retraining, but fundamentally it's a stateless process. You can throw away your current computation state when you're done. And it's multi-user, right? Lots of different people, lots of different services hitting your model at the same time from different environments. DevOps usually manages these servers. They handle the task scheduling, et cetera, all that stuff that needs to happen, the hardware provisioning. And the users and services, of course, are the other group involved in that, the ones who actually need to consume your service. I'm going to include in that application developers, right, as users. They may not be the end user, but really they just care about that endpoint you're giving them. How can I actually make this prediction and get it back? I don't care what's under the hood. That's their point of view on it. This is kind of similar to the actual execution of an application, right? So we have these two sides, building an app, executing an app inside your OS. Now, hopefully your system looks something like this. There's, again, lots and lots of different variations we've seen, but fundamentally, you're training up multiple different models. You're Git pushing them out. Maybe you're using LFS, whatever. You're getting them into some kind of production platform, and you've got an API wrapped around that, and people are calling that API from whatever they like. So we can do this, yes, with just bare servers or rented VMs. Obviously, this works. You configure it right. You pick out the GPUs you need, if you need them, the right CPU settings, right memory. It's pretty laborious, but once you get a pattern down, it's pretty good, until you go and you change to a different framework, and it has completely different needs, and then you have to figure out a different instance type. OK? We build our microservice. For one or two, that's pretty easy. Flask, obviously, is really common. I've seen Node.js front ends, all kinds of stuff. But fundamentally, you're just figuring out, OK, what am I going to accept from the user, isolate it from the model itself, execute the model, pass back my predictions, make sure everything's serializable, all that good stuff. Lots of JSON, DSON, and serialization and deserialization going on there. But then you've also got to figure out, like, OK, how am I going to secure that? How am I going to meter it if I need to actually rate count it and maybe cross-build to other teams? How am I going to disseminate that? How do I let people know about my API other than just my emails out to my supervisor? And then I think about scaling, right? So you can use cloud VMs, for example, to scale. You get very blocky scaling like this, usually hourly, though some of them are coming down. And you repeat that whole process for every different model, each unique environment, et cetera. You can try combining them all into a same server. That works so long as you don't get too many dependency conflicts and you're not dealing with too many languages. It gets pretty messy, or it gets non-ideal when you're using models that have completely different operating characteristics. You don't want to be running your CPU-only models on your high, expensive GPU server, et cetera. All right. How about serverless functions? Well, this is what we would really like, right? Obviously, this takes away all the DevOps. You just are filling out a function body. You get your automatic API wrappers. They're managed by the service provider. You get your instant elastic scaling. You're not worrying about the DevOps. It's a managed service. And it's super cheap. It's build per second. So all of that would be great, except they're not optimized for ML, which means Node, Python, maybe Java, maybe C#, good. Starts to get esoteric. Try to run R. And does anybody know of a serverless R? An R serverless function provider? Right, like not out of the box, right? Okay. Limited dependency support. You can pull down and build your own container and kind of shove that back up into, say, Lambda, and it works. It's a long turnaround. It's kind of annoying, but you can do it. But there's not too much you can do for most dependencies right there. And then if it's something really complicated, many times you can't even shove it back into the service provider. So problems there. And of course, no GPUs. So our deep learning acceleration is out the window, which is a bummer. Max execution time, usually 5 to 15 minutes on most of these service providers, which is pretty cool for my single predictions. Works out fine. Fails horribly as soon as I want to do large batch predictions. I have to pre-segregate my data into these smaller batches, et cetera, regroup it after. And again, speaking to that application experience in Android and iOS, there's no consumer-facing UI. So I can go in as a developer. I can list all of, say, the Lambda or Google Cloud functions I've created. I can expose those to some degree to other people with the right auth. But there's not sort of a way for people to go in, the general public if I wanted them to, or unauthenticated people in my company to go and just say, hey, what are all of the functions that so-and-so has created, and what does each one do, and give me a sample I/O of each and all that. You've got to build that yourself, right? So the no consumer-facing UI is kind of frustrating. So what would we really want if we're to think of like all the characteristics that we want in an OS for AI? And again, a lot of this has been covered already today, which is awesome. We're all hitting the same problems. We're all coming up with the same needs. But some obvious stuff. Broad language and library support, right? I want to use any language I want. I want to use any dependency I want. I don't want the service telling me what I can or can't use. I don't want to have to go and recode something in another framework or in another language just because it doesn't happen to be supported on the platform that I'm using. I want GPU support, of course. I want elasticity and I want concurrency, and I want that to be basically per second so I can ramp up and down immediately. I want an automatic API so that as soon as a data scientist actually puts a model up there, they're not thinking about JSON serialization. They're not thinking about building the wrappers manually. Just drop it in, you've got an API. Good. You want pipelining so that you have this common API across all of your models. So you can pass data efficiently between them, so you can pass results into another. You can run your image recognition, tagging into your NLP, into a scraping routine, et cetera. You want built-in security, because I really would prefer that all the authorization and authentication just be standard across my company and whatever they've chosen, not what that particular developer happens to decide when he creates it. Long timeouts, so if I do want to run batches, I can run for, say, an hour. Versioning and grouping, so I can say, hey, these models, they're visible to like everyone in my working group. These other models, they're visible to everyone in my whole company, et cetera. And old versions, because that prevents breakage. And it also makes it possible for the applications team and the model development team to run asynchronously, so they're not blocking each other. I want it to be portable. So if I decide that I'm going to move from one infrastructure provider to another, I can just pick it all up and do that. I don't have to retrain in a different environment, put those models out there. And I want this discovery and model management UI. So I can actually say, hey, here's an example. Hey, application developer, you just have to look at this one page that's automatically created. All right, so how are we going to build it? So common thread today, of course, containers. Yes. We have our user come in. They're hitting a web load balancer initially, find standard stuff, serving out whatever pages they need to find the model. There's web servers running behind that. When they actually come in and make an API call, that's what I care about. They're saying, hey, I want to make a prediction against sentiment analysis. Right, here's my data. Hit an API load balancer. That finds an appropriate API server in their cloud region. So it's physically close to them, so I'm pulling down on that latency. Inside that cloud region API server, I've got a bunch of containers. Those containers are there. Each one has one of my models in it. Hopefully one's already warm. If so, I just go to that one. If one's not warm already, I get it warmed up. I use it to respond to that request. I optimistically leave it around for a little while unless those resources are otherwise needed in case another request comes in. As my heuristics get better and better, I even start predicting what times of day, what sequence of events might cause one of these individual models to get hit. And so I can pre-warm containers as needed. I can warm up as many as I want, scale horizontally, so I can handle multiple requests in parallel, et cetera. And then I've got once I've got them in containers, all of the usual portability, et cetera, that I would inside those. But it's not just that easy as saying, hey, containerize them all, right? Because as any of us who have tried to do this know, every library and language combination can actually imply a completely different container base that you're going to have to think about, right? Yeah, you can just keep adding them all into one. You get one really big base image, and then it takes a while to shift around, and it's slow to hydrate and all that stuff. So better to keep it kind of stripped down and as light as possible, right? I'm going to build something that just does like my sklearn on with Python. I'm going to do something that just is Java, Weka, et cetera. And then, by the way, for a decent number of those, I've also got to build a version of it that's GPU enabled. So when the user comes along and says, OK, I want to run this model, and this model is using Python, and it's using TensorFlow, and it's GPU enabled, I'm going and picking the right container base to spin up for them, inject their code, and actually execute on top of that. I don't want to be pulling in the non-GPU version and having those CUDA libraries try to hook in when it's only running a CPU. All right. So OK. Once I've got all that, next step, make it really just dead easy for data scientists to add new models. Because this story of like, OK, there are all these great tools out there for containerizing your models, for getting them out there with some framework, that is awesome. If you have enough of a DevOps background, and if you really want to do all of that work to go containerize them all, deploy those individual containers, et cetera. But again, the story I'm trying to follow of pull all that difficulty away so it's really easy for machine learning engineers to just deploy out there without thinking about it. Well, that says GUI and easy APIs, right? So you want to create a new algorithm? OK. You pick your language. You give it a name. You tell me whether it's open or closed source. Tell me whether or not you need GPUs. And you say, OK, create. All right. Step one. We'll follow that same serverless environment workflow, right? Next thing you get, web IDE. You've got the option to clone it down if you want. Every individual algorithm you create has its own repo, so you can edit with your own web IDE. That's fine. But also for convenience, you can just step into the web IDE, paste your code right in, and hit build. Specify whatever dependencies you want. So now I'm going to create a new base as you specify dependencies, and I'm going to go and retrieve those for you. I'm not going to make you go and create the container locally and re-upload it. You're already on a server configuring stuff, so why shouldn't it just go and do the pip call and put those in for you? So whichever language you happen to be in, make it possible for you to add dependencies the way you naturally do in that particular language, and the server takes care of the rest, right? And then you specify the visibility, public or private, specify whether or not you want to have, say, a royalty on top of it, specify what version number you're releasing on, et cetera. Good. And you publish. There you are. Everything under its own namespace, so no conflicts. You have your own user namespace. You're not going to hit other people. And then you can take these things that you've deployed out there, We're going to add some more features here, get into the nitty gritty, right? So pipelining, I talked about this abstractly. What do I really mean? All right. In Unix, you can just say, OK, I've got one or two different programs, and I can literally pipe between them, right? So I can say, hey, cat, get the text out of the file, pipe that into some shell script I've written to extract keywords, pipe the results into some ranking algorithm I've written, et cetera. And it's just join them together. All right, let's use that same syntax. So I have, say, an algorithm which does keyword extraction, util keywords. And I just pipe the file into it. And that gives me some set of keywords out. I've got another model that I've written, which is a ranking model. I just say, hey, into version 1.0 of that, pipe the keywords I got from the former algorithm, et cetera. So sending data from one model to another should be this easy, right? Obviously, you can add other logic in there if you need to otherwise chop up the data in some way. Intelligent orchestration, right? So since we're aware of all the models that are in the system, and since we're aware of all the containers and when they're spinning up, now we can start actually looking at their execution paths and doing really smart things, right? So from one of these algorithms, I have now a mechanism for piping to others, and it's embodied in code, so I can see when it occurs. And this means that I can start predicting that when someone goes and they call one top-level algorithm, they're going to be calling algorithms B and C pretty darn soon. So what am I going to do? I'm going to start pre-warming those whenever I see that call come in for that top-level algorithm. So the bottom of the chain is already warm and ready to run by the time it's filtered through the top of the chain, right? And you can look at lots of other stuff. You can start looking at time of day. You can start balancing your compute and memory so that as you get data on how these have run in the past, and you can say, oh, well, this particular algorithm uses a decent amount of memory and it only uses the CPU, and this other algorithm uses X memory and it uses a GPU, and I happen to have a machine available which has, a good enough CPU and a GPU attached and enough memory to satisfy both. Then when I see that both of those algorithms are about to be called, I can stack those containers into that particular piece of hardware, instead of having to just expand out further. And so what I'm doing now is I'm actually getting much, much better efficiency on the hardware that I'm provisioning, because I'm tight packing all these individual containers in a way that makes sense for those particular models. All right. Let's standardize our versioning, right? So why shouldn't models have semantic version on them? Why shouldn't I be able to pick any version of a model and execute it ad hoc, right? So anytime you put a model into the system, anytime you publish it, that version is then callable at any time. There's a historic record of every single one you've ever published. When I actually make an execution, I'll say, yeah, OK, I'm going to be calling Algorithmia HQ/PyTorch demo there in the red box. And I can just say at call time which version I want to execute, right? Because it's the one that I know. If I wanted to, I could leave that off and just call latest, yes. But the advantage of always having those named versions available is that now your application developers are sitting there, they're waiting for something to do. You've put a model out there, you've said, OK, version 1.0 of this is good to go. They're like, OK. They start integrating that into their code. They start actually deploying this application out into the world. It's version locked. You go ahead and you iterate. You create your 1.1. You create your 1.2. You create your 2.0. You tell them whenever one of them is ready and good. But then they can version whenever they want, whenever they're ready. So you're not sitting there step-locked on each other and blocking each other from doing work. You can also have different versions of the model that might be appropriate for different contexts, right? One really fast but not particularly accurate one that's going to be used maybe more by mobile users because latency is going to be more important there. One accurate but slow one that's going to be used for your batch predictions. They're just two different version numbers. You're good to go. And then logging and analytics, of course, right? So being able to look at latency, being able to look at resources used, how much capacity is actually available in your overall systems, or are you going to need to add more machines? Having that authentication, you know who's actually calling what at what time. What this lets you do is not just your standard DevOps stuff, because yes, you want to actually know that like your hardware is running good, there aren't big blips, you're not seeing weird surges. But you can also start pulling things out like, OK, what teams are actually using the models I've created? Was this particular research path I went down useful to other people in my organization? right? Are there models that are sitting there unused? And maybe then other development teams can come along and say, oh, yeah, those really aren't getting utilized as much as they should. Maybe we should start putting them into some of the other things we're developing, et cetera. You can use this to justify the time and money you've actually put into building models because you can show usage. You can use it to do billing and chargebacks between departments if that's how your team is monetized, et cetera. And you can understand if the investment that's actually been made in particular pathways of research is really paying off in real usage across your organization. All right. And then I'm going to talk about the abstraction layers just for a minute, because there's certain ones that should be visible and certain ones that shouldn't, right? So you basically want, every different infrastructure provider there has, different compute characteristics, slightly different APIs for how you provision stuff, how you auto scale it, how you do your load balancing, what kind of remote storage they're using. But we want that to be invisible and consistent across our platform. So from the model developer's point of view, all they know is they put it in there, they write some wrapper code for doing the prediction, and they get back a result. They don't actually care what it's running under. There is one case where you care, which is simply file systems, right? So in the same way that if I'm reading from, who remembers floppy disks? If I'm reading from floppies, I'm addressing A://. If I'm reading from a hard drive, C:// I could be reading from a network file system, NFS, et cetera. Same thing. I can get files from anywhere, and I can just prefix it with the service provider. But otherwise, everything's the same. It's still in some folder. It's still got some name, et cetera. So when I migrate from one platform to another, all I have to change is the service identity at the beginning. And then lastly, what about that outbound UI for my application developers, right? So app devs can come in. They can say, hey, all right, let's search through a catalog for everything that does sentiment analysis of some sort and get back a bunch of results. When I see one of them, I can click on it, and I can get a full description there put in place by the data scientist who actually developed it, by the model developer. I can then go and run an example right there inside the UI, so I can actually be testing these models before I'm actually pulling down any code and actually figuring out which one I want based on the text shown, based on real-time execution of that model with whatever data I happen to toss into the UI. Then, once I'm happy with it and I know it's the one I want, clients in every language, so that all I have to do as an app developer is say, well, I'm developing my React app, right? So I'm just going to click on the JavaScript segment. I'm going to copy the JavaScript code required to execute that algorithm, and I'm just going to drop it into my app. And that's all the app developer needs to know about how to execute your model, aside from what the actual input structure should be of the data that they're sending, right? And let's keep that fairly consistent across our different languages. But at the same time, let's also provide like an actual REST interface if you need to do something else. And then what we did is, after building all of this, we took this, we made it algorithmia.com so that hobbyists, people who just want to serve one or two models, who want to do fun stuff, they can put it out there, and they can actually have that available for anybody else to execute. And we've seen some really cool stuff with this. Researchers that, at the end of building their paper, take their model, they put it up on Algorithmia, they send that link out with their paper. So now someone who gets interested in what that paper is about can actually go and live execute it. Because while it's cool to have a repo and be able to pull down that code and retrain the model the same way to validate it, really what most people want to do is just see it in action and try it out, right? But we also add the ability on top of that to have royalties so that individual data scientists who are developing models who do want to monetize it can actually sell right on top of the platform. But then also take that platform and make it something that can be deployed in any enterprise organization, right? Because there's really great frameworks, again, out there, and if your DevOps team is invested enough to figure out how to do that, to build it, and to spend their time managing it, great. But if you want something that's going to be low code, easy to manage, managed infrastructure, but running in your own private cloud so it's secure, that's what Algorithmia on-prem is all about. If you do want to talk about any of those, by all means, come talk to me after. If I can have like 2 minutes, I will show you very quickly. Not even 2 minutes. If you do want to actually just try this out and see how fast it is, because you can go to bit.ly/algodev and drop into digit recognition, and what you're going to find there is just simply a repo where you can click on digit recognition, you can copy the requirements.txt, you can copy this base code inside algo.py, and you can download this pre-trained model. And I'm not going to try here because the network latency has been ridiculous, but I promise it's going to take you under 2 minutes to actually go from having that pre-trained model there to having an actual executable algorithm on algorithmia.com that you can then hit that endpoint, right? And it'll scale as needed. OK, so I'm gonna stop there and give you this slide in case you want to get in touch with me at all. And as to whether we have time for questions, I don't know. I know we're on break.
We're on break, so we could go questions.
Yeah. OK, so I'll just hang out, and then I won't be offended if you want to leave and go get snacks. All right, thanks.